Hello, everyone. Welcome to section 3.2, part 1. This section is on polynomial functions and their graphs. So first off, what is a polynomial function? So polynomial function is a function of the form. And usually we use like a capital P of x, P for polynomial, and they're going to be of the form. So we've got some a sub 0 plus a sub 1 x plus a sub 2 x squared plus all the way up to a sub n x to the n. So here p of x is a degree n polynomial function. Okay, so the a sub 0, the a sub 1, a sub 2, all the way up to the a sub n, so those are all numbers. And then you've got x as your variable. So we've talked a little bit about polynomials already. So now we're just looking at them as functions and diving more in depth onto their behaviors. So I also briefly before talked about the basic graphs of polynomials. So let's review those. So look at their graphs. Basic polynomials. So the most basic polynomial, besides I guess just the constant polynomial, is just the y equals x line, which, as we've seen before, looks like this. And then we also have our standard parabola, y equals x squared, which looks kind of like this. Cool. We also have, we keep increasing degrees, a basic cubic here. So that's a x to the 3. And that kind of looks like this. I don't like that second line. There we go. And then if we go up another degree again, we get something that looks like y. So y to the 4th. And so that might look like, so it's going to look like, as we've talked about before, it's going to be parabola, but it's going to be more like squared off base. So instead of the really rounded parabola, we've got something that maybe looks like this. And then let's see one more. If we increase one more degree, so we've got y equals x to the 5th, we're going to see it looks a lot like y equals x to the 3rd again, but this time it's going to have, again, sort of more squared off. And these aren't perfect drawings. If you want to see a more accurate representation of these polynomials, I recommend you either Google them or look at them in the book. But this is kind of the basics of what they look like. So there's this kind of alternating pattern, and we will expand on that here in a minute. But before we do, just a note. So to graph basic polynomials, we can use the above graphs that we just made and function transformations. So for example, if we wanted to graph maybe this polynomial function, say we've got x minus 3 to the 4th plus 2. This isn't in the standard form. As we've seen up here, it's not in sort of this sort of format right here, but it is still a polynomial function if you expand it out and everything. And so we can look at the basic graph. So we've got a degree 4 here. So we're going to look at, we're going to base it off of the yellow graph right here. And what we note is that, so note that this thing is f of x equals x to the fourth. And then we've added a 2 to the outside, so shifted up by 2. And then the minus 3 on the inside there is right by 3. And so if we started with our yellow graph, which looked kind of like this, when we want to graph this, we just take the yellow and we shift it up by 2 and right by 3. So let's actually get some tick marks going on here. And so if the vertex is here at 0, 0 to begin with, it's going to be shifted up by 2 and right by 3. So it's going to land about right here. And then it just kind of looks like that. Cool. So yeah, so if you have the basic sort of setup for these polynomial functions, you can easily graph some of them, at least with function transformations, if you have them in the right sort of form. But what about graphing other polynomials, maybe things that are more complex and things that you can't really get to by easily seeing a function transformation? And that is most polynomials. You're not going to be able to just graph them by looking at them and kind of going off of the basic graphs that we did. So we're going to get a couple tools in our arsenal in this first part that we're going to see are going to help us with graphing general polynomials in the second part of this section. So the first tool that we're going to use is end behavior. So end behavior basically means we want to know what happens to our polynomial function p of x as x goes to infinity. So we want to know what happens to p of x as we get x bigger and bigger and bigger and bigger. And we also want to know what happens as x goes to negative infinity. So x gets bigger and bigger and bigger, but it's negative now. So more and more negative, more and more off to the left side of the graph. Okay. So here is the rule for understanding behavior of polynomial functions. So say we've got p of x equals, so we've got our a naught plus our a1x plus an xn. So let's say we've got some polynomial that looks like this. Then here's the rule. I'm going to make a chart. So and so it's going to depend on whether or not we have odd degree or even degree. And so degree, remember, is this n right here. So this is going to be whether n is odd or n is even. And then it's also going to depend whether an is positive or an is negative. And an is this an right here. It's the coefficient of the highest degree x. And so now what happens is, so if you've got odd degree and an is positive, as x goes to infinity, p of x goes to infinity as well. And as x goes to negative infinity, p of x goes to negative infinity. Okay, but if an is negative, then as x goes to infinity, it flips. P of x goes to negative infinity, and as x goes to negative infinity, p of x goes to infinity. All right, and if you have an even degree, it looks a little different. So as x goes to infinity, p of x is going to go to infinity. But as x goes to negative infinity, p of x is also still going to infinity. And then if an is negative, it's going to flip again. And we see that as x goes to infinity, p of x goes to negative infinity. And as x goes to negative infinity, p of x still goes to negative infinity. And this is a lot of symbols and data, and it's easier to kind of see what's going on in pictures. So if we were to draw the exact same chart, but this time we'll graph it, it'll make a little more sense what's going on. So we have our 4 cases. When we look at pictures of what's going on, so if we have odd degree and an is positive, we're going to get something that kind of maybe looks like this, which is why as you go further right, it gets bigger and bigger, and further left, it goes more and more negative. And then if an is negative, then it flips it about the x-axis in a way, and you might get something that looks like this. So as you go more and more negative, more and more off to the left, it goes up and up and up, and vice versa. And then if you have an even degree, what you get is like a U or like a W sort of shape. So if an is positive, you're going to get maybe something that's like this. But both the arrows are going to be pointing in the same direction. And then if an is negative, both the arrows are going to be pointing in the same direction, but they're going to be pointing down. So maybe it might look like this. Okay, so that's the chart in pictures. So we can use this to determine the end behavior of a polynomial. So let's see an example of that. So determine the end behavior of, and let's do p of x equals, I don't know, something weird, like negative 2x to the 5th plus 3x squared minus, I don't know, 364. So to determine the end behavior, all we need to look at, remember, is the leading coefficient and the degree. So first of all, an in this case is negative 2, and that's negative. And then if we look at the degree is 5, and that is odd. So if we look at the end behavior, so as x goes to infinity, we just go back to our chart. And so we've got negative leading coefficient, odd degree. So we've got this case right here. And so as x goes to infinity, the polynomial goes to negative infinity. And as x goes to infinity, or sorry, as x goes to negative infinity, p of x goes to positive infinity. All right, so pretty straightforward once you kind of have a chart like that. Now remember, our end goal is to be able to start at least sketching graphs of polynomials in general. And so looking at the end behavior is one way to do this, so we know where the arrows should be going. But the next tool that we're going to cover is finding the zeros of the roots. Same thing, just 2 different words for it. So a zero, or a root, if you prefer, of a polynomial function, call it p of x, is a value c such that p of c equals 0. And for this class, for our purposes, c needs to be a real number, so no complex roots. Now, if you remember, we found these for quadratics. And the 2 main ways we did that were, by factoring and using the quadratic formula. Okay, so if we do kind of the same ideas that we used earlier in this course, finding the roots of polynomials isn't actually too bad. So just a little refresher, let's see an example. So let's find the roots of, and let's do something maybe a little more different than what we've seen before. So let's do like negative x to the fourth minus x cubed plus 2x squared. Now, right off the bat, you're probably looking at this and you're like, this is a degree 4 polynomial. How on earth am I supposed to factor it? We didn't cover any factoring methods that dealt with it. But let's take a step back and let's just see what we can do. So the first step is to let 0 equal this. So we want to solve for x where p of x equals 0, right? And so what you're going to notice is that in each of these terms, we have an x factor. And in fact, in each of them, we have at least 2, because the smallest one is x squared. So we can write this. We can pull out an x squared from each of these terms, right? And so we get x squared equals negative x squared. So pulling out the x squared minus x plus 2. And I'm also going to pull out the negative just to make it a little bit easier. So this becomes negative x squared, and then we'll get x squared plus x minus 2. And so now what we can do is we just need to focus on factoring this, which we know how to do. We can just use many different methods, but I'm just going to use the AC method today. And so we've got this equals AC equals B. A is 1 and C is negative 2, so that means it's negative 2, and then B is just 1. And I think that the two numbers that'll fit into this, 2 times negative 1 is negative 2, and 2 plus negative 1 is 1. So this thing underlined in yellow is going to be, we'll write it out, it'll be x plus 2, x minus 1. And so when we go back to our original derivations we're doing, we get negative x squared, and then the thing in parentheses becomes x plus 2, x minus 1. And now we know we can look at it. So our zeros are at, and we've got 3 different sort of things going on. We've got this negative x squared. That's going to be 0 just when x equals 0. We've got this x plus 2, and that's going to be 0 when x is equal to negative 2. And then we've got this x minus 1, and that's going to be 0 where x is 1. And that was using, again, the zero product property. All right, so that's how you find the zeros of polynomials. You just use factoring / the quadratic formula. The factoring is usually a little bit cleaner to do. But there's nothing wrong, of course, with the quadratic formula. But anyway, so this is, again, another tool that we will use for graphing polynomials in general, along with the end behavior that we discussed earlier. And the reason that I talked about using transformations to graph basic ones is because sometimes if I ask you to graph it using the zeros, using the end behavior, et cetera, you can use the transformations to kind of see like, oh, do I kind of have the general correct shape? Am I on the right track? Anyway, practice these skills. After practice, they will become easier and easier. And if you have any questions on anything in these lectures, as always, I'll see you in office hours.